forgot about that.
All right, guys, quiet down. So
We never finished the part.
I know. So let's work on that. So field lines leave positive charges and approach negative charges. In the absence of the opposite charge, charges stretch towards infinity. All lines must make 9-degree angles with lines of equal potential, which can never cross. Right? Therefore, all lines. Okay, let me just explain what this means in pictures. Okay? So, the field lines always leave positive and always go towards negative. So this is positive and that's negative. Does that make sense? Right? They must always make 90 angles with the surface. Which means if I do a start here, they also have to start at a 90-degree angle from the surface. 90 degree from the surface. 90 degree from the surface. 90 degree from the surface. Are you with me? They always make 90-degree angles with the surfaces. Correct? Now, why? Because right? Because they actually make 90-degree angles with lines of equal potential. That means lines of equal potential are always, it says in the paragraph, are always parallel with the surface. So, if the lines of equal potential are always parallel with the surface, and these lines always make 90-degree angles with the surface, that means that the lines also make 90-degree angles with the lines of equal potential. Alright? So that means that at every single point, the lines of equal potential must be drawn in a way that they always make the 90-degree angles with the field lines. Okay? Now, we already did this. This makes the lines tend to form circular shapes. And lines are denser when the field lines are stronger. So if you have a particle that has more charge, all they're really going to do is to increase the number of lines that you draw to symbolize the fact that there is more charge. So this positive charge is a lot more positive than that negative one is negative, since it has more. Does that make sense? That's how you show that it has a little more charge. Alright, so let's fill this out. You have to have it in the Behringer thing. Coulomb is a unit of charge. The unit of electric force is the Newton. The unit of electric field is, who knows? Newton divided by Coulomb, yes. The volt is a unit of potential. Electric volt is a unit for energy or work or electric potential, which is analogous to the joule. Okay. So then, now you have to finish this part. So, draw an illustration that shows the following field patterns. Right? So the first one, from a sphere with a charge of E. That's the first question in the quiz. So if the sphere has a charge of E, it just looks like this, what we have there. And it goes towards what? Infinity. And then, for B, a sphere with a charge of negative E. So how does that look like? Just like that. Does that make sense? So we already did those, so we went quickly. Now, between two spheres with a charge of E and negative E. So it will be what's in the board here, except I have to finish it. It would be something like this. Notice that the field lines curve like that. This is what we were talking about in that paragraph. Alright? The idea is, alright, field lines, well, this should go to the top. It's always symmetric. The field lines can never cross each other, and they always must make 90-degree angles with lines of equal potential. Right? So just kind of like that, dipole moment. You're not supposed to be crossing, so this actually goes to infinity and then back around. And then go like that. It goes really far and then comes back. You see what I'm saying? You can do a small scale of that, right? But you see what I'm talking about? It's kind of like a butterfly shape. Does that make sense? Circular shape. And then if you draw the, if you were to draw the equipotential lines here, they would always have to make 90-degree angles with each one of those surfaces. And they do. Every single line has to make a 90-degree angle with that equipotential line, right? So I'm going to open this document that I have that kind of talks about these things before we continue here, because I already have them all in like a. So if you ever lose this or forget this and you're trying to review for the test, I have on the drive a folder that has a picture of all of these patterns that we're talking about right now. So you can just follow along right now, and then later on, if you need to find it, you know where it is. So it's on the electric fields and potential folder. And then if you go, I think it's under practice. No, it's not there. It's supposed to be something that says notes. Podcast. It's not going to be a podcast. It's not going to be a math. So let's go to the first electrostatics and see if it's there. Practice. No, I guess it's not there. Interesting. I swear to God, I used to have a place. Well, we'll Google them and then, just so you can see it. So I'm going to Google an electric dipole, which is what this is called. By the way, you should write on the bottom of your drawing that that's what this is called, because if it shows up in the test and they say electric dipole, that is what that's called. So an electric dipole, all right, will look like that. That's it. That's what we drew, right? You see the shapes that I try to do the board? That's a little nicer, right? I'm going to try to find one that has the equipotential lines also, so you can see that. So you see, I like this one because it shows you what a field is. Look at the arrows. You see the arrows? They are there to represent what the force. And you see one of these circles then. They are lines of what? Equal potential. And at all points, the field lines must make 90-degree angles with that. Are you with me? So that's kind of show you that as the dipole moves around, the field moves around it. Correct? Pretty cool. So it's an electric dipole. Very awesome one. So here's another one that kind of shows the same idea. I don't know if it moves or not. Yes, it is. That's the same one. All right, so that's this is an actual lab, an experiment that simulates the electric dipole, right? So you can see that on that. So the next question says, how would this look different? Okay, so how would this look different if we were talking about a charge of E and E? So then now they're both the same charge. Okay, so let's see how that looks like. So now if you have the same charge, I like this one because it shows the difference between an electric dipole and one that's repulsive, right? So you see, when you have attraction between them, the field lines are continuous from one to the other. You see that? You see? They're all continuous, right? But in this case, you see how they kind of, it's almost like the fields bounce off each other, and you can see why that causes repulsion. Does that make sense? Right? Because they bounce off each other and they're forced to go apart. Now, if you were drawing lines of equal potential, I'm going to try to find, with the potential lines, a drawing that has them. So let's see if we find one. Look, this is another example. See how they bounce off each other? You see that? That's what you're trying to draw for that letter. Remember, you're supposed to have this in your drawings. Ooh, this is a good one. Let me show this one. Save that one for later. I'll talk about that one. I'm trying to find one that has the lines of equal potential so you can see them. I think this one does. There you go. Oh, that's a dipole. I don't want a dipole. All right, there you go. That one shows that. Right? So we have two negatives, but it's the same idea. It's a repulsive field. How is this different? By the way, I think that's the next question. So let's look at that. It says, oh no, that's not there. But the only difference between the picture that we saw with the two positives and this one that has the two negatives is that the arrows here point in instead of out. Does that make sense? But you still have the same repulsive pattern in the middle. Does that make sense? Now notice the lines of equipotential. Notice how at every single point they make 90-degree angles. Right? And since the field lines are curving, the lines of equipotential have to curve too. But also notice the middle. What's the potential at the middle? 0. There's no line there. Why is that? Well, remember the formula we talked about last class, right? Potential equals change in U by Q. But the change in U, by definition, right, is force times distance. So force is electric force, right, times distance, D. Now remember that E is the force per unit of charge. So that means if I can replace force here with EQ. Force equals EQ. You see that? Right? So then I can put this as EQD. Right? EQD. Now therefore, if there is no electric field, like there is no electric field here, you see that there's no field lines, then there cannot be a change in potential energy. Does that make sense? But if there is no change in potential energy, there can be no change in potential. Does that make sense? So they kind of all feed into each other. So that it makes sense. We talked about this. No field, no potential. However, just because you have no potential, it doesn't mean you have no field. It doesn't go backwards because that depends on charge. Right? We talked about this in the last class. But either way, I was just trying to show you how there is no potential in the middle because there's no field in the middle. Right? Because it's repulsive. Right? So that's the answer for this question. Make sure you have a diagram that looks like that. How does it look different now if I make one of the charges double the charge? So it looks like this. That's why I said I was going to use this picture. Remember that charge is represented by having more field lines? So you see, what do I know about this charge versus this charge? It's more what? More positive. It's a bigger positive charge. So maybe this is 2Q and this is Q. Are you with me? Now, what that does is you know how they repulse each other? That pushes the repulsion a little more towards this guy than that guy. It's almost like this guy pushes harder. Does that make sense? So that in the middle of the place where the field doesn't happen is a little push more towards this way. So if this was Q and Q, at the middle you would have no field. But if this is 2Q and Q, it's kind of pushed this way a little bit. It's kind of like Earth and the Moon. Where's the center of gravity between the two of them? Not really in the middle, a little more pushed towards the Moon because gravity of the Earth is more pulling. Does that make sense? Than the Moon's pull, right? So if you have the Earth here and the Moon over here, if you were right here, you fall towards the Earth, right? So you got to go here, close to the Moon, to not fall towards either. Does that make sense? Because the Earth's gravity is bigger than the Earth's gravity of the Moon. By the same token, when something is pushing, it's going to push more towards the one that, away from the one that pushes more. Does that make sense? This is the opposite idea. If you have a charge that has a bigger negative force than the other, it would be just like the gravity of the Moon example I just gave. Since this one pulls more, right, the location of the middle, so like for example, if it was negative and negative, the point at 0 will be right between them. But if this one is negative 2Q, then that shifts the entire thing a little more towards the head. Does that make sense? The pulling, the repulsion. Now what we have here is the actual question that they're asking you to draw, which is E, right? What they have E here is a charge that's more positive than this one is negative. And I can tell because there's more field lines, correct? They're denser. Okay? So what happens? It doesn't look like a regular dipole. It looks like a little more, dense on the positive side than the negative side. And of course here you have the exact opposite. So this will actually be the answer for these two will be the answer for these next two over here, which is E and F. E is saying the negative is more negative, and then F is saying the positive is more positive. So it will be, this will be F and this will be E, right? So this is E and this is F. So you just draw something that looks like it so you can remind yourself. But the whole point of having this there is to teach you how the field pattern looks like, because you're going to need that for the test. All right? All right? Everybody clear? So what do we learn when we see this, all of these arrows together like this? We learned that what? That this one is more bigger charge. Magnitude is bigger, right? And then if we have just the two charges, and this has more field lines, and they're both the same charge, that means that the center, where the field is 0, is going to be pushed more away from the positive, because positive pushes. This one, since negative pulls, the center is pulled towards the negative, since negative pulls. And that one is more negative. Does that make sense? All right? Okay. This all matters, by the way, when you're trying to understand electricity and the way things behave, like a proton orbiting around an electron. So that's where it becomes important. All right. Now, check this out. They also want you to do, for part G, two positive ones with one. So this one here will be G. That would be G. All right? Which one? One is more positive than the other. Okay? So then, if you guys want, right, and you want to do this later, complete your thing later, you're supposed to complete it. You're not supposed to be working on something else. If you want to be doing this, you can, I can leave it here for a second, take a picture of it, and then you can fix it. That would be probably the best idea. But you need to have these drawn on your notebook thing. All right? You guys want to take a picture, or just remember it? All right? So what was it? This was E, F, and this is G. All right? Why is it important to have this on the barometers? Because then before the test, you can go over it and review it. Because that's what's going to be on the test. The question will be about these things. All right? Barometers are a good way to study for the test. You got it? All right, moving on. So the next question says, between two, we already did this one. It's a repeat of this one, you see? So there's no H. Okay? But one thing I want to show you, though, that's an additional one that I kind of want to show you, is this. Check this out. Look at these. These are all the cool patterns. So we already saw this. This is the dipole, right? We saw this. This is a repulsive pattern. And this is a pretty cool one because it's also showing the lines of equipotential in there with the dotted lines. This is what would happen if you had a plate and the charge. So it's kind of like combining. Remember, the plates, the lines just leave the plate, correct? Like this, right? If it's, well, this is negative, right? The lines would just go towards the plate. Are you with me there? But the positive charge, they're going to go all around it, right? So when you combine both ideas, you get something like that. And you see how the equipotential lines look as well. This is super interesting. And I'm going to leave it here because we're going to talk about it in a second. This is about a lightning rod and how they work. We'll talk about that in a second. All right? So, okay. Let's continue here and we'll get to the lightning rod question. Vector versus scalar. Now think about this. Who has the sigils? So make sure you start. Everybody gave her the sigils? No? Because if you don't give her the sigils, you can get no legals. All right? Give her the sigils right now. If you don't have the sigil, give it to her. Hopefully we can finish this. Okay, so. That's a lot of fucking stuff. We're not starting circuits today. Fuck that.
What?
There's no way we're going to finish this thing. Alright. This stuff is hard. So, vector versus scalar. Now remember, what is the difference? Next person. Where is it? Stefan. Remind us of what a scalar and a vector are again. What's a vector? What does a vector have that a scalar doesn't have?
A vector has direction.
Direction. So all you have to ask yourself, does this thing have direction? Right? So, electric force. With next person. You gotta be ready. Anna, does force have direction? Yes, so it's a vector, right? Electric field. Next person. Does that have direction? What did you say? Altara. Does field have direction? Think about it. What? Look at the arrows in the board. Of course it has direction. All right? Look at the arrows in the board. All right, so yes. What about potential? Remember, the lines are represented by these dotted lines. That is a number of where you're at. Does energy have direction? Does energy have direction? Yes? No? Next person? One. No, one. You're right. What about potential energy? Does that have direction? No. Okay? So it's potential energy, and then like both of them are scalars. How about charge? Next person. Ms. Nauman? Does charge have direction? or is it a value of how much positive or negative you are? So it's a scalar. All right? Good. 6. A system consists of two charges, a negative one and a positive one. You see that? If it runs out. What is the net charge of the system? This is important. So think about an atom, a hydrogen atom. Okay? It's got a positive proton and a negative electron orbiting around it. All right? So then it says, what is the net charge of the system? Easy question. What's the next person? Justin. 0. All right? What is the electric field produced by it? Is there electric field in the system? So is the field 0? We saw how this looks like. It's on the board. So if the electric charge, what is the net charge of this system? Is the field 0? Or the net charge is 0? You see what I'm saying? So there can still be a field even if there is no net charge in the system. Does that make sense? Make sure you understand that. It's important, okay? All right? Now, does your answer depend on the separation between the charges? Let's think about that. We need to put the formulas. We need to put the formulas on the board so we can help us out, okay? So for the rest of the day, we're going to be looking at these things. So the formula for electric force electric, is K, Q1, Q2 over distance squared. Field is described as force divided by charge. Therefore, you write it like this, K1 over D squared, right? Potential energy is field, right? Force times distance. Force times distance. Or, since force is E times Q, you can also write U times Q times distance. Which, basically, if you multiply this by Q and by distance, you get K, Q1, Q2, distance. Potential equals change in energy divided by charge. Right? So therefore, it's just this thing divided by charge, so that you can say it's ED, right? Or you can just say it's going to be K, Q1 divided by charge, so got rid of one of the Q's, divided by D. All right? Now, these are all the formulas we need for this chapter so far. Now, the question asked, does the field, whether the value is 0 or not, because that's what we're asking, is the field 0? We said no. Does that depend on the distance between the particles? Whether or not the field is 0. Let's think about it. Can the field ever be 0? So long as there are charges. Think about it. Can the field ever be 0? Does the formula say that? No matter how far you go, it's still going to be something. Now at some point, it's going to be so small that it doesn't matter, correct? But it's never 0. Think about that, all right? Now, the force experienced by a charge at a charge 1 at a point A. So let's write what that means. So there's a charge 1 here, and that's located at point A. So this is a point A, a location of that charge, right? Is different in direction and in magnitude from the force experienced by charge 2 at point B. So I have a second charge at a second point. So what I know is that the force that charge experienced there is different both in direction and magnitude. So what I mean is that you could have something like this, and then this could have something like that. So you know they are experiencing different forces, both in direction and magnitude. Does that make sense? And then they ask you, can we conclude that the electric fields at points A and B are different? So the force is different. Can you automatically conclude that E is different? So let's go to the formula because it'll help us out. So two things are experiencing different F's. Right? Can we conclude that E is the reason why the E is different if the F is different? Can we automatically say that? That is different for two different things. Therefore, that must be different for two different things. Is that necessarily true? Why not? Because the Q. So the charge matters, correct? Do you see how you have to dissect these problems when you're doing the test? Because that's what shows up in the multiple choice. This is hard, okay, guys? This is not an easy topic. So you make sure you think about it. But it's easy. The question was actually not that bad. Now, so we cannot conclude. Can we conclude the electric fields of point A are different? No, because we don't know anything about what? The charges. And then you put the formula there. E equals F over Q, which proves that point. All right? Can an electric field exist in a vacuum? There's nothing in between two things. Can it still exist? Did you learn anything about whether or not the electric field needs something to go through? No. In fact, it does exist in a vacuum because it's carried by electromagnetic particles, the photons, that can travel through anything. So, yes, absolutely, they can exist in a vacuum. It is independent. It does not need a medium to travel through. Right? Now, by the way, what is between? Think about this very carefully. This is the proton and an electron inside of a helium atom. What's between the proton and the electron? What's between that? Think about that. Ever thought about that? So you have matter here. You are made of atoms, right? What's between the atoms? Just empty space, yes? But what's between the positive charge, the proton, right? Now, so that means, what would you call that empty space? Would you call it maybe a mini vacuum? Right? By the way, side note from modern physics. There is no such thing as nothing.
Oh my God.
Okay?
Let's not do that.
Hold on. The space between a proton and an electron is not actually empty. If you were to watch that space over time, things pop in and out of existence without any explanation or reason. Now, this is really cool stuff. This is called quantum plasma fluctuation. The idea is that empty space, every second, a particle forms, but the cool thing is at the very same second, an antiparticle forms. And so matter and antimatter collide with each other and annihilate each other. So that means you made something and you immediately unmade it. So long as it doesn't last very long, it's fine. It doesn't break thermodynamics laws. Right? So in other words, you know that rule of energy can be created and destroyed? Right? That's true over long periods of time. But in a microsecond, something can just pop out into existence. And that's fine, so long as it what? Pops back out. So that means the empty space between here and the sun, the empty space between the atoms, the empty space between protons and electrons, even the empty space between quarks inside the proton. Because in proton, that's quarks, right? All that empty space is not really empty. Every second, things just pop in and pop out of existence. Now, this thing's insane, but think about this is a little bit of cool stuff. Quarks, these particles which are popping in and out of existence, are waves trapped in the space-time by the Higgs boson. We talked about that before. But because they're waves, they have a finite space that they need to occupy. That means if you have a very, very close space between two things, not anything can pop in there. Only things that can fit there. Does that make sense? Right? Meanwhile, outside of that, larger things can pop into existence because there's space for them to pop into existence. Are you with me? You can't pop into existence here if you're huge, because you're between two things. Are you with me? Which means, if you got two metal plates and put them really close to each other, only very small wavelengths can form there. Outside, bigger wavelengths can form, which means bigger things form here, on average, than in here, on average. This causes a kind of pressure that pushes the plates close together. So, it sounds like mumbo jumbo. How can things pop in and out of existence? But the fact that two plates will approach each other, people say, but gravity would have done that. Gravity would have put the plates close together because they're both fast, right? Yes, it's true. But even if you account for gravity, you still don't understand. They go faster than gravity should push them together. What's pushing them together is these virtual particles popping in and out of existence, because outside they are more massive than they are inside. Now, the really cool thing about this is black hole. So now, a black hole is right here in this thing. And one of these particles pops into existence right there. Its antiparticle pops inside a black hole. Now we have a problem. Because you know they're supposed to annihilate each other the next second, correct? This particle, though, has to fall towards the black hole and it cannot get out. This one is outside the black hole, so it doesn't get out. It does get out. So you just made a particle. And that breaks the rules, right? So then the black holes cause a problem for the whole theory. So that means black holes don't exist. So this is actually, when we thought about quantum plasma fluctuations and we figured out that it was true, it created a problem for the theory of black holes. So the current idea is that people don't think that event horizons are really real. Because if they were, that would mean that black holes would be an impossibility in physics. There's a bit of a convoluted theory that tries to conciliate this problem. And the idea is that if this is true, that black holes is really emitting particles over time. Are you with me? Because these particles just pop into existence. So it looks like the black hole is just emitting particles over time. But since that can't happen, that means the black hole must be losing mass. Which means over time the black hole evaporates. Some crazy ass shit physics. Alright? It's because it's creating particles, right? But it can't create a particle out of nowhere because it breaks the rules. So therefore, it must be losing matter. That means black holes over time just get smaller and smaller and smaller until they disappear. What? By absorbing matter, correct? So, hey. This is exactly interesting. I thought black holes expanded by absorbing matter. So yes, if there's stuff near the black hole, and it gets unlucky, and too close to it, it falls into it, correct? Now, okay. Hold on, inside the black hole. Right, I see. Okay, hold on. That's true. Guys, bear with me. That's true. But what I'm saying, separate from that, and the fact that black holes are gathering matter over time, there is the fact that because quantum plasma fluctuations happen everywhere in the universe, every second, the event horizon of the black hole causes a problem. Because particles will form in and out of it at the same time, but the one that forms in cannot annihilate the one that forms out because they are separated by an event horizon from which this particle can never escape. Because nothing can move faster than the speed of light that's necessary to get out of the black hole. That prevents a problem because you're creating matter in this now. If the rule says you can create temporarily, but if you create permanently, you're breaking the rule. Does that make sense? Therefore, this means the rule will be broken. But since the rules can't be broken, that means something must be happening to the black hole. Since it's producing this, it's as if the black hole is making this particle, right? That means the black hole must be losing particles and therefore shrinking over time. Which means every single black hole would cease to exist over time. Very tiny ones will disappear in a very split second. So we actually want to try to make black holes inside a large hadron collider. Some scientists are trying to design experiments to make that happen. If that happens, right? If that happens, it will be so tiny they will evaporate in seconds, according to this theory, right? So, but if we make a huge black hole, an enormous one, will take so long to evaporate, and it's called evaporation, but it's not the same kind of idea, right? That it will actually take longer than most galaxies will last for a black hole to actually cease to exist, the big ones. And therefore, while we say black holes will evaporate over time, the supermassive ones are going to last as long as the universe lasts, because it takes forever for that to happen. Does that make sense? Who's going back to the thing? All right. Why? We already did this. Why can electric field lines never... we talked about why potential lines can never cross, because that would mean you'd be at two different potentials in one place. But why can't field lines never cross? Now, remember what field lines mean. What the field lines mean is that if I put a positive particle here, it will move this way. Correct? Now, what would it mean if it had arrows crossing? What would that mean for that positive particle? It moves is going what? Think about it. What field? I'm going to say again, by definition, field lines is the direction that a positive particle would follow in that place. Now if I had a field line crossing another, what would it mean at this point? What would the positive particle be doing? Two different things. Can you do that? So that's why they can't cross. Alright? Okay. So, two charges are separated by a finite distance. Okay? Somewhere between them, on a line connecting them, so let's do that, So there's two charges. I don't know anything about whether they're positive or negative, but they're separated by a finite distance. Somewhere, guys, pay attention. This is like practicing for the test. Like seriously, this is the kind of question that show up in the test. All right. So in a line between them, somewhere in the line between them, the net electric field is 0. So somewhere there is no field. E is 0. Remember the lines we drew earlier today. So think about what that means. What do you know about the charges? So they have the same or the opposite charge. They have the same charge, right? Remember the drawings that we did? Okay. Now, if the point is closer to charge 1, what does that mean? So, by the way, we established that they're either both positive or either both negative. But if that point where E is 0 is closer to 1 than it is to 2, what does that mean? It depends, actually. It means that either 2 is more positive than 1, or 1 is more negative than 2. Does that make sense? Got to make sure you write that down what I just did. Okay. Now, you see this scenario over here. We got a positive charge, another positive charge, and a negative charge. They're asking you, is there a place, right, in this situation where the field is 0? Now let's think about it. Positive pushes and positive pushes. If it was this, just these, this does not exist. Is there a place where the field is 0? No. We saw it, right? If it's this doesn't exist. Is there a place where the field is 0? No, just these two. They're both positive. Is there a place where the field is 0? Yes, there is, between them. Remember that? Right between them. Okay, so now that's there. We suddenly add a negative charge. What does negative do? Pulls or pushes? So what do you think is going to happen to the location of where the 0 is? It's going to move towards the negative. But it doesn't make sense to go on this side where in between these charges is just a field that goes this way. Right? So therefore, all that does is it pulls this a little bit to the left, somewhere around here. Does that make sense? All right? Think of it this way. When you have multiple, we have to actually talk about that. If you have multiple particles, the effect of each is additive. This is called superposition. Check this out. Very important. You're going to be the test for sure. I put adding vectors. So if I put a positive charge here, a negative charge here, and a positive charge here. Are you with me? Then I ask you, now I'm going to put another positive charge here. What will happen to it? Well, let's think about it. It wants to go towards this one or away from that one? Away from that one. By the way, they're all the same charge and all equally distant from each other. Okay? What about that one? Is it going to go towards it or away from it? Towards. So it will go towards it. What about this one? Towards or away from it? Away from it. So it will go back. So that means what is this particle really going to do? You're going to add all those arrows together and figure out the direction it's going to go, right? So it's kind of like, remember how you do vector addition? You put the arrows next to each other? So you'd have to draw this one there, and then that one there, and the resultant one would be like this. Does that make sense? So it will go towards the right. Does that enough? Let's do another practice like that. All right? So you have a positive one here, a negative one here, a positive one here, and a positive one here. What is the direction of the net force that acts on this particle? Let's think about it. You have to do charge by charge. Let's start with this one. What is this one doing to that one? Repelling or attracting? Repelling. What is this one doing to that one? Attracting. Now, here's where you got to be careful. This is a square. It's further from that one than it is from this one. Are you with me? So the effect here is stronger. Does that make sense? That means I would have to put a bigger arrow to remind myself that the effect is stronger. What about here? It will also push it that way. Either way, to figure out what's going to happen, I have to add them all together, right? So then I just draw them next to each other. I would have to go outside the board to do it, but it would be that plus up, so it's going to go something like this. Does that make sense? You add them all together, it's going to go in that direction. And so the way this shows up in a test is that they will have something like this, and each of these arrows is an option. A, B, C, D, E, and F, and they say which of them is the right direction for the direction of the particle, the net force of the particle is. With me? So that's kind of how that works. We're going to do one more, make sure you know how to do it. All right, so let's see. You're going to put a positive one here, a negative one here, a positive one here, and a negative one here. What is the net effect of that particle? So let's see. One, is it attracting or repelling here? Attracting or repelling? attracting. So I draw this towards the left. What is the effect that this one has on this one? Attracts or repel? So what I have to draw towards it, right? What about this one? Attracts or repel? Oh, sorry, these two, sorry. Repel, right? So then I have to put one going there. Right? And then I just have to add the vectors and see which direction it goes, right? So then what you do in your head, you would put the arrows next to each other, right? And then the solution will be connecting them like that, right? Does that make sense? So you just add vectors. That's how you do it, okay? Now, either way, we already did 13, so let's do it really quick. Explain why electric fields from inside conductors can affect the outside, but not the other way around. So we talked about this already. I'm going to do it again. If you have a positive charge inside of a conductor, by definition, arrows must leave it. If this is true, this creates a negative charge on the inside of the sphere, which makes sense because the lines are hitting it, correct? But if that's true, it makes a positive charge on the outside of the sphere, which means lines leave it. Yes? That essentially looks like the field left. There was a positive field inside and a positive field outside. So it basically looks like the field left. Are you with me? When we do the other way around and there's a field outside, remember we talked about this? What that does is it polarizes this has to be negative because the lines are entering it, right? And that has to be positive because the lines are leaving it. But if that's true, inside you have a reverse field. Correct? And so since you have a field one way and a field the other way, they cancel each other out and there's no field in the inside. Correct? This is called electrostatic shielding. So that's the answer for the entire question. All right? I would literally draw what I just did here, right? I wouldn't completely erase what's happening inside so you can remind yourself what's happening. But there is a polarization effect which basically cancels the field out of the inside, and therefore you get no field in the inside. And this is called electrostatic shielding. So you can send a signal from inside a conductor, but you cannot receive one. Does that make sense? We did that with aluminum foil last class. Remember that? Okay. Now, 14. In a certain region of space, the electric potential is constant. So potential is not changing. So we know this delta V here is 0, right? The electric field must be positive, negative, or 0. So let's see. This is 0, therefore this is 0. In a certain region of space, potential is constant. So there's no change in thing. What do you know about E? Let's think about it. We know this is not 0 because it's a region of space. See the question say in a certain region of space, so we know D is not 0. Are you with me? So there is a distance over which this is acting. And you know delta V 0 when this number is not 0. So that means E has to be 0. That means the only way you don't change potential is if there is no field or if you stay in an equipotential line. Are you with me what I'm saying? Okay. Remember that? That's why if I am staying in the equipotential line, the D is 0. I'm not moving, right? And that's why it's going to be 0. So either the field has to be 0 or you're not moving perpendicular to the field. So if you have equipotential lines, there's a plate, right? We did this last class as well. So you have a plate. So if there's a field, there's a change in potential unless you don't move with respect perpendicular to the field, right? But if you move parallel to the field, the D is 0. Because D means how much you move with the field. Are you with me? So if D is 0, change is 0. The other way for the change to be 0 is for it to be no field. Does that make sense? So since the question says there is a region of space through which you're moving, right? But there is no field, therefore the change in E must be 0. Right? Guys, alright. Now we did this one as well. An electron accelerates from rest through a region of potential difference V. So there's a region with a potential distance V. And the electron is accelerating from rest. Now remember, what does this mean? If this is positive V and this is negative V, right, that means the field is coming this way, correct? And they mean the change is V. Okay? And a proton does the same over a region of negative V. Right? So you're doing the same thing. How do the final speeds compare? We don't have a formula for this, but I'll help you out. Isn't this energy right here? Correct? U is energy. So there's a relationship between V and energy, correct? All right, so look at that. So V equals energy divided by Q. So it's like the charge doesn't really matter. But remember, there's another way to energy. Change in potential equals change in kinetic. Remember that? Therefore, I can write this as mv squared over 2 as well. Right? Now you have something that you can do. Right? So they say, you do an electron over a region V. It gets a certain speed of it. Let's get a certain speed. You do the same thing with a proton over a region of negative V. Right? Well, you'll get the same V at the end. Well, let's think about that. First, we have to think about that charge. If the electron, right, if the electron has a field V, the electron has a charge negative here, correct? So whatever V happens here, you're going to have a negative charge here. So this whole thing here is going to be negative, the change in V, right? If you have a proton with negative V, the proton is positive, but that was negative V, so this is also going to be negative. So as far as the sign is concerned, it's the same. Now let's think about something else. The charge, the amount of charge. They have by definition the same charge. So that should be the same. So now all there's left to figure out the V is M. Except protons are 1,820 times more massive than electrons. So if the proton has more mass, it has more inertia. So of the two, which one resists a change in velocity more? A proton or an electron? Which one? The one that has more inertia. Right? So that means the electron should be going faster at the end. That's shit crazy. That's like AP physics. Right? But anyways, that's the one I wanted to get to. Why are lightning rods pointing? Right? So we had a picture of this right here that we can go look about. So notice what happened with the lightning rods. Thank you. Right? What happened? Those are empties? All right. You see the lightning rod over here? Because of its shape. Now remember the rule that the field lines must always be perpendicular to the surface. Correct? That forces all the field lines to be like this, which forces the field lines near the tip to be really close. Are you with me? You see how the lines appear to get denser and denser towards the tip of the lightning rod? Even if I erase my lines, you can see that pattern. What do denser lines mean? More charge. So what is the lightning rod trying to do to charge? Think about it. Not cancel it out. On the contrary, it's trying to what? Concentrate the charge, yes? Now, why would I want to concentrate the charge in that little spot? Think about it. So there's a cloud up here that has a positive charge, and then a lightning rod that's trying to concentrate the opposite charge over here. It's trying to attract it so that it doesn't hit other places. It hits there. So the pointy shape of the lightning rod concentrates the field lines to make it more likely that the strike happens right there. Does that make sense? All right? So that's pretty cool stuff. All right? So this explains why lightning rods work. It's not because they're tall, although that also helps. Lowering the distance helps. Right? Because think about it. If I lower the distance with the same E, all right, so I make this number smaller with the same E, I would affect delta V as well. But, are you with me what I'm trying to say? You guys follow that? Very good. Almost done. So, 17. Why do conductors shield? We already did this. 17 is a repeat, so skip it. Skip, repeat. 18. If the electric field is 0, then the electric potential is also 0. We did a question like this before. If the E is 0, V is 0. True or false? E is 0, V is 0.
False.
Because of D. You have to know about D. Alright? So you can make sure. So it's false because of D. Now, two charges, Q1 and Q2, are separated by a distance R. Oh, this is one of those typical problems. If the charges, magnitudes of both charges is double, what happens to the field? So, I am doubling both charges. what happens to the field strength? Let's see if you guys get this. So I'm doubling both charges, not the distance. Not messing with the distance, just doubling both charges. What happens to the field? People win instead of quadruple. But the formula only has one charge in there. It just doubles. So it's a trick question, right? So watch out. Look at the formula and be careful. Only because you know how it's force divided by charge? So it's only the charge that causes the field that matters, not the charge that's receiving the field. Alright? Explain the amount. By the way, this is analogous to gravity. On the acceleration of gravity, only the masses being orbited counts. Acceleration is the same for whatever mass. Remember that? No matter objects of different mass fall the same way. Likewise, two different charges experience the same E. Alright? Due to another charge that's causing the E. Alright. Explain how the amount of energy is arbitrary, but changing energy is not. We already talked about this earlier in the year. If I say how much energy I have here, so let's talk about this in terms of field. Right? So if I say this, I actually mentioned this last class already. So if I say this is 0, and that's 10 positive, and that's 10 negative, I could also say it the same way, that this is 0, and that's 20. Correct? So the amount of energy, 20 or 10, is arbitrary. Correct? But if I move from here to here, it's always going to be a change of 20. Does that make sense? Yes? So the actual amount depends on where you pick the 0 to be. Correct? But the change is not arbitrary. It's always the same thing no matter how you set the 0. Right? If I go from here to here, it's a 20. If I go here from here, it's a 20. But the value is arbitrary. But the change is not. That's what that's showing. Okay? I know you guys are tired. Almost done. Alright. So state whether the point midway between two charges would be a maximum, a minimal, or neither in terms of potential. So I want you guys to imagine this, okay? So let's put a potential graphs here. By the way, next class, remember, it's practice for this topic. Potential graphs. Okay, so there it is. This is a graph of electric potential. Okay, there's a lab that I do with AP Physics where we collect data to actually make this graph. But the point is, negative is down. Are you with me? Positive is up. So positive 15 volts creates a hill upwards. Negative 15 creates a hill downwards. This is like getting those equipotential lines and making them look 3D. So if I was looking at this from the top, it will look like circles, the way that we saw them before. Are you with me? So, with that in mind, the question that's being asked here is this. A point between two opposite charges. So that's this picture right here. A point between the two charges. Is that a maximal, a minimal, or neither? Is that the maximal of the graph, the minimal of the graph, or neither? It's in between, so it's neither. Are you with me? Alright. How about this one? Two charges, if they were both positive, we will have two hills instead of a valley and a hill. Are you with me? So you have a hill and a hill. So the point in between them, a maximal, a minimal, or neither? A minimal. Does that make sense? Now, if I had two negatives, I will have two valleys. So the point in between them, a maximal. Does that make sense? Alright. Easy. Almost. Alright. So we have a charge. We do not know. We only have potential lines. We have no field lines to do this. Okay? But we have, this is positive 160. That's the negative 160. Which one is the positive charge? Where is the hill? Left side or right side? Left side or right side, the hill? Left side. You should not be packing yet. Right? So, what is the direction of the field at point D? Towards the right or towards the left? The field. If you were to draw the field line, would it be going this way or that way? At point D. The field goes from positive to negative, so it will be going towards the right. That's A. Now, what time is it? We still have a shitload of things to do. We'll continue next class. Shit's hard, man. There's a lot to cover. Next class, practice day for fields. Ignore what the calendar says. We're doing practice day for fields next class. Alright?